Right now, you believe you're experiencing the present, this moment, this breath, this second. You believe the past is gone and the future hasn't happened yet. But what if every one of those assumptions is wrong? And not just incomplete, fundamentally wrong. Because when physicists began studying time with extraordinary precision, they uncovered something so unsettling that it challenged one of our deepest intuitions about reality. The moment you call now may already be behind you. The past may never have fully disappeared, and the future you're waiting for may already exist. This is the story of how science discovered that time doesn't work the way we instinctively believe it does. Let's begin with something you've probably never questioned. Every morning you wake up, you move through your day, and the entire time you feel an invisible current carrying you forward, second after second, minute after minute, always in one direction. We call it the flow of time, and it feels as undeniable as gravity itself. Why wouldn't it? Everything in your life seems to confirm it. You were born, you grew older, you remember yesterday, but never tomorrow. Coffee cools, ice melts, stars burn, people age. Every experience tells the same story. Time moves, and it only moves forward. For thousands of years, humanity built its understanding of reality on that simple idea. No one expressed it more clearly than Isaac Newton. To Newton, time was absolute, a universal clock ticking silently in the background of the cosmos, the same for everyone, everywhere, on Earth, on the moon, even in the most distant galaxy, one shared present, one universal rhythm, one cosmic clock. It was elegant, it explained everything people observed, and for more than 2 centuries, almost no one questioned it, until the universe revealed something extraordinary. Newton wasn't just slightly mistaken. His picture of time was fundamentally incomplete. But before we discover why, consider something even stranger. Right now, you feel as though you're experiencing this exact instant. You're not. The light reaching your eyes takes a tiny amount of time to arrive, and the electrical signals traveling through your nervous system take even longer. Then your brain spends roughly 80 milliseconds transforming those signals into conscious experience. By the time you're aware of this sentence, it already belongs to the past. Every conscious moment you experience is slightly delayed. Your brain simply hides that delay so perfectly that reality appears seamless. You've never actually experienced the present exactly as it happens. You've only experienced an incredibly convincing reconstruction of it. Think about what that means. If your own brain quietly manufactures the feeling of now, how certain can you be that now even exists the way you imagine? That question would eventually find its way to a young patent clerk in Switzerland, and his answer wouldn't simply change physics, it would change reality itself. That question found its answer in an unlikely place. In 1905, Albert Einstein wasn't a world famous physicist. He wasn't even a university professor. He worked as a patent clerk in Bern, Switzerland. By day, he reviewed inventions. By night, he quietly wrestled with a question that almost everyone else had overlooked. What would you see if you could chase a beam of light? At first, the question sounds almost childish. Common sense tells us that if you run fast enough, you'll eventually catch up, just like one car pulling alongside another on a highway. Match its speed, and it appears almost motionless beside you. Surely light should behave the same way. But nature had other plans. No matter how fast you move toward a beam of light or away from it, light always travels at exactly the same speed, about 186,000 miles per second. Every observer, every experiment, every single time. It doesn't matter whether you're standing still, flying in a spacecraft, or racing through the galaxy. Light never changes its speed. At first glance, that seems impossible. Imagine sprinting towards someone as fast as you can, only to discover they're still moving away from you at exactly the same speed as before you started running. It defies everything our everyday experience tells us. Most people would have assumed something about the experiment was wrong. Einstein did something different. He assumed the experiment was right. And then he asked a far more unsettling question. What if the speed of light isn't what's changing? What if time is? That single question transformed physics forever. Because if the speed of light is truly constant, then reality has only one option left. Space and time must become flexible. They must stretch, compress, and bend. To understand why, imagine the simplest clock ever built. Not one with gears or springs. A clock made from two mirrors. A single beam of light bounces between them. Up, down, down. Every complete journey is one tick. Simple. Now place that clock inside a spaceship traveling close to the speed of light for the astronaut inside, and nothing changes. The light still travels straight up and down, tick, tick, tick. Everything feels perfectly ordinary. But now imagine watching that same spaceship from Earth. While the light travels upward, the spaceship keeps moving sideways. From your perspective, the light no longer travels in a straight line, it follows a longer diagonal path. And here's where reality becomes extraordinary. The speed of light cannot increase, it is fixed always. So if the light must travel a greater distance without moving any faster, there is only one possibility left. Each tick must take longer. Not because the clock is faulty, not because the mirrors move, but because time itself is passing more slowly inside the moving spaceship. This effect has a name, time dilation, and despite how impossible it sounds, it is one of the best tested predictions in all of physics. In 1971, physicists carried ultra-precise atomic clocks aboard commercial aircraft and flew them around the world. When those clocks returned, they no longer matched identical clocks that had remained on Earth. The difference was tiny, only fractions of a second, but it matched Einstein's predictions with astonishing accuracy. Time itself had flowed differently, and this isn't just a laboratory curiosity, it's happening above your head. Right now, the satellites that power GPS orbit Earth at enormous speeds. Because of both their motion and their distance from Earth's gravity, their clocks tick at a different rate than clocks on the ground. Engineers must correct those differences continuously. Without those corrections, your phone's location would drift by several miles in a single day. Every time you open a navigation app, you're relying on the fact that Einstein was right, your GPS works, because time does not. Most people assume relativity only matters near black holes or in distant galaxies, but you're experiencing it every moment of your life. Einstein wasn't finished. 10 years later, he made an even more astonishing discovery. Motion isn't the only thing that changes time. Gravity does too. Massive objects don't simply pull on other objects. They reshape the geometry of space-time itself. The stronger the gravity, the slower time flows. Even on Earth, this effect is measurable. Your feet are slightly closer to Earth's center than your head. That tiny difference places them in a slightly stronger gravitational field. As a result, your feet age just a little more slowly than your head. The difference is unimaginably small, but modern atomic clocks have measured it, even across a height difference of less than a foot. Think about what that means. There is no single clock governing the universe, no universal presence shared by everyone. Your now and someone else's now are not guaranteed to be the same. Newton imagined one cosmic clock. Einstein revealed something far stranger. Every observer carries their own, and each one can tick at a different rate. Follow that idea to its extreme, and you arrive somewhere that feels like science fiction. Imagine traveling to the edge of a black hole, not crossing the event horizon, but hovering just outside it, where gravity becomes almost unimaginably intense to you. Perhaps only 1 hour passes. Your heartbeat feels normal. Your watch keeps perfect time. Nothing seems unusual, but when you finally return to Earth, years or even decades may have passed. Everyone you left behind has grown older. Some may no longer be alive. You haven't frozen yourself. You haven't escaped time. You've simply traveled through it at a different rate. This isn't speculative physics. It's a direct consequence of Einstein's theory of general relativity, one that has been confirmed again and again through observation and experiment. Time travel into the future isn't science fiction. It's part of the universe we already inhabit, but that leaves us with a question even stranger than the answer. If time can slow, stretch, and flow differently for different observers, then whose now is real? Is there a single present shared by the entire universe? Or have we been imagining one all along? Because when physicists turn from the vastness of space to the microscopic world of atoms, they uncovered something even more unsettling. Something that doesn't merely bend time. It challenges the very idea that time flows at all. Everything we've explored so far belongs to the world we can see. Planets, stars, galaxies, spacecraft, the universe on its largest scale. But when physicists turn their attention inward to atoms, electrons, and particles smaller than anything we can directly observe. They discovered a reality even stranger than relativity, a reality so unfamiliar that Einstein himself struggled to accept it. Because down here, nature no longer behaves the way common sense says it should. Imagine watching a single particle, not after you've measured it, but before. According to standard quantum mechanics, the particle isn't simply hiding a definite position waiting to be revealed. Instead, it is described by a range of possible outcomes. Only when a measurement is made does one definite result emerge. Exactly what this means remains one of the deepest debates in modern physics. But every successful experiment points toward the same unsettling conclusion. At the smallest scales, reality behaves very differently from the world we experience every day. That alone is extraordinary. But then physicists asked an even stranger question. What role does time play in all of this? The answer led to one of the most famous thought experiments in modern physics. It came from a man named John Wheeler, a physicist who worked with Einstein and mentored Richard Feynman and helped shape much of 20th century theoretical physics. Wheeler asked a question so unsettling that it almost sounds impossible. Can a choice made now influence how we describe what happened earlier? To understand why he asked this, we first need to understand something remarkable about light. Sometimes light behaves like a wave. It spreads across many possible paths, interfering with itself, producing beautiful patterns that only waves can create. Other times, light behaves like a particle, a single localized event, one path, one detection. The remarkable part is this: which behavior appears depends on how the experiment is performed, not because light changes its mind, but because different experiments reveal different aspects of quantum behavior. Then Wheeler imagined something extraordinary. Suppose a photon begins its journey long before the final measurement is chosen, only after the photon has already entered the experiment. The observer decides what kind of measurement to perform. Classically, that choice shouldn't matter. The photon's history should already be fixed, its journey already complete. But quantum experiments refuse to follow that intuition, beginning in the 20th century, and confirmed in increasingly sophisticated experiments, including a landmark realization in 2007. The results consistently match the predictions of quantum mechanics. The measurement chosen at the end determines which description successfully explains the entire experiment. At first glance, it almost feels as though the present is reaching backward into the past, but this is where we need to be careful. Nothing in these experiments allows information to travel backward through time. Nothing lets us rewrite history. Nothing violates causality. Instead, the experiments reveal something much subtler. Our everyday intuition about when quantum properties become definite may simply be incomplete. The clean boundary we imagine between before and after becomes surprisingly difficult to define at the quantum level. And that may be even stranger than actual time travel, because it forces us to reconsider what we really mean by the past. Just when physicists thought reality couldn't become more mysterious, another discovery appeared, one that Einstein openly disliked. He called it spooky action at a distance. Today, we know it as quantum entanglement. Imagine creating two particles together. Their quantum states become linked, then separate them. One remains here on Earth. The other travels, in principle, to the opposite side of the galaxy. According to everything we expect from ordinary life, they should become completely independent. Yet repeated experiments show something remarkable. Measure one, and the correlations between both particles appear instantly. Not because a hidden signal raced between them faster than light. No experiment has ever demonstrated that. Instead, their shared quantum state behaves as though distance alone cannot fully describe the relationship between them. Einstein believed that this couldn't be the final story. Surely, he argued, there had to be hidden variables, some deeper explanation, some missing layer beneath quantum mechanics. For decades, physicists searched for exactly that. Then, in 1964, John Bell proposed a way to test the idea experimentally. Bell's theorem transformed a philosophical debate into something science could measure. Over the following decades, experiment after experiment produced the same answer. Most decisively, the pioneering work recognized by the 2022 Nobel Prize in Physics confirmed that nature behaves exactly as quantum mechanics predicts. The universe does not obey the kind of local hidden variable picture Einstein hoped for. That doesn't mean faster than light communication exists. It doesn't. But it does mean reality is more deeply interconnected than classical physics ever imagined. And think about what we've uncovered. Relativity tells us there is no universal present. Quantum mechanics challenges our intuition about when physical properties become definite. Entanglement reveals connections that ignore our ordinary expectations about separation, piece by piece. The comfortable picture of reality begins to dissolve. And once enough pieces disappear, a new question naturally emerges. What if time isn't moving at all? What if the flow we experience in awe isn't a feature of the universe, but a feature of us? That idea may sound impossible, yet it leads directly to one of the most fascinating interpretations of modern physics, one that changes not just how we think about time, but what it means for the universe to exist. So far, every discovery has pointed in the same direction. There is no universal clock. Time doesn't pass at the same rate for everyone. The quantum world refuses to fit neatly into our everyday intuition. And yet, the deepest surprise may still lie ahead. Because when physicists followed these ideas to their logical conclusion, they arrived at a picture of reality unlike anything humanity had imagined before. It's known as the block universe. At first, the name sounds almost disappointingly ordinary. The idea behind it is anything but. Imagine your favorite movie. When you watch it, each scene seems to appear one after another. The story unfolds. Characters are born. They grow older. They change. Eventually, the film ends. But that's only how the movie appears to someone watching it. Inside the film reel itself, every single frame already exists. The beginning, the middle, the ending. None of them are waiting to be created. They're all there simultaneously. Some physicists believe space-time may work in a remarkably similar way. According to Einstein's theory of relativity, space and time aren't fundamentally separate. Together, they form a single four-dimensional structure called space-time. Within the mathematics of relativity, the past, the present, and the future are treated far more symmetrically than everyday experience suggests. From this perspective, every event in your life occupies its own location within space-time. Your first breath, your first day at school, this exact moment, your final goodbye, not appearing one after another, but existing as different locations within the same four-dimensional reality. If that's true, then the present isn't a universal feature of the universe. It's simply the moment your conscious experience happens to occupy. Like the beam of a flashlight moving across an enormous landscape, the flashlight creates the impression that only one place exists. But the landscape was already there, long before the light arrived. This idea is known as eternalism, or more commonly, the block universe interpretation. But this is where scientific honesty matters. The block universe is not an experimentally proven fact. It is an interpretation. One possible way of understanding what Einstein's equations may be telling us. Many respected physicists find it compelling. Others disagree. The mathematics allows the interpretation. Nature has not yet told us whether it is the correct one. Even so, the idea fascinated Einstein. When his lifelong friend Michele Besso died in 1955, Einstein wrote a letter to Besso's family. In it, he reflected on the meaning of time. He wrote that, for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. It remains one of the most famous sentences Einstein ever wrote, not because it proves the block universe, but because it reveals how deeply relativity had changed his own understanding of reality. Yet one profound mystery still refuses to disappear. If every moment exists, why do we experience only one at a time? Why can't we remember tomorrow the way we remember yesterday? Why does every story appear to move in only one direction? To answer that question, physics turns away from clocks, away from relativity, and towards something far more ordinary. A cup of coffee, a melting ice cube, a broken glass, a messy room. At first glance, these things seem unrelated. In fact, they all reveal the same hidden law. A law that quietly governs nearly every process in the universe. Physicists call it entropy. Entropy is often described as a measure of disorder. More precisely, it measures how many different microscopic arrangements produce the same overall state. That definition sounds abstract, so let's picture something simpler. Imagine building a perfect sandcastle. There are only a limited number of ways the grains of sand can come together to create that shape. Now imagine the castle collapsing. There are almost countless ways for those same grains to end up scattered across the beach. Order is rare. Disorder is overwhelmingly more likely. The same idea appears everywhere. A hot cup of coffee cools, it never warms itself, an egg can be broken, it never spontaneously rebuilds itself. Smoke spreads through a room, it never gathers itself neatly back into the chimney, not because the fundamental laws forbid the reverse, but because the reverse is unimaginably unlikely. This gradual increase in entropy creates something remarkable. It creates the arrow of time. Here's the astonishing part. Most of the fundamental equations in physics don't actually distinguish between past and future. Run them forward, run them backward. The mathematics still works. The equations themselves have almost no preferred direction. The direction we experience comes overwhelmingly from entropy. As disorder increases, we perceive time moving forward. Our memories point toward lower entropy. Our future points toward higher entropy. And that's why yesterday feels different from tomorrow. Not because physics demands it, but because the universe began in an extraordinarily ordered state. Nearly 13.8 billion years ago, the observable universe emerged from conditions of remarkably low entropy. Ever since, entropy has been increasing, like a tightly wound spring, slowly releasing its stored order. Every memory you've ever formed, every heartbeat, every sunset, every civilization day has unfolded along that one long thermodynamic journey. So perhaps you aren't drifting down a river called time. Perhaps you're witnessing the universe gradually evolve from extraordinary order toward ever greater complexity and disorder. And your experience of time is simply what that process feels like from the inside. So let's return to the question we began with. You believe time was a river carrying you relentlessly forward. Perhaps it isn't. You believe the present was a single shared moment experienced by everyone in the universe. It isn't. You believe the past had disappeared and the future had yet to arrive. Modern physics paints a far more subtle picture. Relativity tells us there is no universal now. Quantum mechanics challenges our deepest intuitions about measurement and reality. And one interpretation of space-time suggests that every moment may exist within a single four-dimensional structure, not waiting to happen, simply waiting to be experienced. Notice what science has done. It hasn't answered every question. It has transformed the questions themselves. For centuries, we asked, what time is it? Today, physicists are asking something far stranger. What is time, really? And remarkably, we still don't know. That's one of the most beautiful things about science. The deeper we explore reality, the more mysterious it becomes. Every discovery reveals another question waiting beneath it. Every answer opens another door. Perhaps that's exactly how knowledge is supposed to grow, because the greatest discoveries rarely arrive by confirming what we already believe. They begin by quietly dismantling it. Now consider one final thought. If every moment of your life has its own place within space-time, if your childhood, this conversation, and the person you will become decades from now are all part of the same cosmic structure, then somewhere within that structure, the future version of you already occupies its own place. Not because fate has been proven, not because free will has been disproven. Neither conclusion follows from today's science, but because in one serious interpretation of modern physics, the future may be no less real than the past. Whether that picture ultimately reflects reality, what we still don't know, and that's an important distinction. Science advances by testing ideas, not by treating every compelling possibility as fact. The block universe remains an interpretation, one of several. Its greatest value isn't that it settles the mystery, it's that it forces us to see time in a completely different way. And perhaps the universe isn't continuously creating new moments. Perhaps every moment already belongs to the architecture of space-time, while consciousness experiences them one after another. Or perhaps reality is stranger still. The truth is, we simply don't know. But whatever the final answer turns out to be, one thing is already certain. Time is far more extraordinary than human intuition ever imagined. It stretches, it slows, it depends on motion, it depends on gravity. It shapes every experience you've ever had, yet remains one of the least understood features of reality itself. And perhaps that's the greatest surprise of all. The closer we come to understanding time, the more it seems to challenge our understanding of existence itself. So maybe the deepest mystery isn't whether time flows or whether the future already exists. Maybe the deepest mystery is why the universe allows conscious beings like us to ask the question at all. Because every equation we've explored, every experiment we've discussed, and every theory we've followed has led us to the same place. Not certainty, wonder. The universe is under no obligation to match human intuition. And time may be the clearest reminder of that truth. The next time you glance at a clock, remember, it isn't simply measuring time, it's measuring one of the deepest mysteries humanity has ever encountered. One we're still trying to understand, one that continues to reshape our picture of reality itself. And this journey is only beginning because once we question time, another mystery immediately appears. If time isn't as fundamental as it seems, then what is? What is the universe actually made of? Not atoms, not particles, not even space and time themselves. At the deepest level of reality, what truly exists? That's the question we'll explore next. And it may be even more surprising than time itself. Until then, keep asking impossible questions because history has shown that today's impossible question often becomes tomorrow's greatest discovery.